Thank you very much, then, everyone, for joining. As I said, please let us introduce to you the CLIMRES Capacity Building Program with the kickoff of the Integrated Solutions for Climate Resilience, a CLIMRES Webinar Series. My name is Telmo Jiménez Irizar, and I will be moderating today's session. As we are all aware, due to numerous causes that we don't have time to cover in exhaustion today, the whole world, and specifically talking about Europe, is unfortunately experiencing a moment in history in which the frequency and the severity of extreme weather events is significantly rising. When defining a more concrete scope, the Mediterranean region showcases the devastating consequences of climate-related disruptions. Because of this, in this first webinar, we will cover urban heat, wildfires, and earthquakes risks and hazards in cities, and with the focus on the work and the tools being developed and implemented by the CLIMRES pilots of Barcelona and Athens. So without losing more time, we will begin by giving an overview of the CLIMRES Resilience Solutions, followed by a multi-hazard vulnerability assessment, and delve later into the two pilots. So to begin with, I give the floor to Carla Rodriguez Alonso, architect and researcher from Cardiff Technology Center. So please, Carla, when you're ready, you can begin.
Okay, thank you, and good morning, everyone, from my side. So before we explore the individual solutions applied to the pilot sites, I would like to introduce the CLIMRES project briefly and explain how it contributes to the resilience of buildings and urban areas. So the CLIMRES project develops digital resilience solutions that help cities assess, understand, and manage climate-related and multi-hazard risks that affect buildings and urban areas. So our objective is not only to understand vulnerabilities, but also support the decision-making and identify practical actions to improve the resilience before, during, and after the disruptive events. So the CLIMRES approach is built around three complementary pillars that you see there. So the vulnerability assessment methodologies that allow to evaluate how the exposed and vulnerable buildings and urban areas are to different hazards. Then the inventory hub of climate resilient buildings, which provides a digital catalog of adaptation and resilience measures. And then the decision support toolkit. So this transforms data and assessments into actionable information for planners, authorities, and other urban stakeholders. So together, these components help to bridge the gap between the understanding of the risk and implementing the resilient solutions. So to ensure that the solutions respond to real-world needs, CLIMRES is developing and validating the services into pilot sites across Europe. So in Barcelona, the focus is on heat waves. In Athens, the focus is on resilience to wildfires and earthquakes. Then in Senigallia in Italy and in Ljubljana in Slovenia, the focus is on flood resilience. And then we have a replication site in Compiègne in France to explore multi-hazard resilience for buildings in the design phase. So yes, in this first webinar series, we will dive into the Barcelona and Athens pilots. So now I will briefly present the CLIMRES ecosystem of services which support the resilience and planning at different levels. So at the foundation, we have the inventory hub for climate resilient buildings and the data management platform. These provide access to a set of resilience measures and also enable the integration and management of heterogeneous data sets. Then we have three levels of services, so strategic, tactical, and operational. level. At the strategic level, we have the strategic decision support system that helps stakeholders assess vulnerabilities, risks, and resilience performance. Then we have the tactical level services, which are specialized services with focus on specific hazards. So this includes urban heat resilience, flood resilience, structural and seismic resilience, and also fire resilience. Finally, at the operational level, we have the smart evacuation service to support preparedness and emergency response activities. So one of the key strengths of the we will see today related with the mentioned pilots, the inventory hub and the urban heat resilience, which are linked to the Barcelona pilot site, and also the structural and seismic resilience and the fire resilience, which are linked with the mentioned Athens pilot. So now just to highlight that one of the key strengths of the project is that it supports decision making at different governance and operational levels. So at the strategic level, the services helps users to assess vulnerabilities, understand risks, and prioritize long-term interventions. At the tactical level, the stakeholders can analyze specific hazards, evaluate adaptation options, and support preparedness planning. And at the operational level, the tools contribute to emergency planning, preparedness, and response activities, and also helping stakeholders in this way to act when a hazard occurs. So by connecting these different levels, CLIMRES enables a more integrated and proactive approach to climate resilience. And this is all from my side for the introduction.
Thank you very much, Carla. That was very good. And next, we have a GIS specialist and industrial engineer currently working at ICCS, the Institute of Communications and Computer Services. Jason Dimitriou, he will present the multi-hazard vulnerability assessment. So when you're ready, the floor is yours.
Excellent. Thank you very much. Let me share my screen really quickly. Okay. Can you see my screen? Excellent. So, good morning from my side, Kalimera. My name is Jason Dimitriou, and I want to present you briefly our contribution to the project regarding the horizontal methodology of vulnerability assessment of buildings through different hazards. Today's presentation has been built in ArcGIS story map, which is easy to navigate and hosts interactive maps. As Carla mentioned, in the CLIMRES project, we are dealing with multi-hazard assessment and the resilience and operation of buildings under stress during these hazards, how vulnerable they are to earthquake, flood, urban heat, and wildfire. The pilots that the CLIMRES project is responsible for assessment is the Barcelona pilot for the urban heat, two suburbs of the Athens for the wildfire and earthquake in Greece, the Senegalia and Ljubljana for the flood resilience services, and yeah, here it is, and in Paris, the replicator of the multi-hazard assessment. So, in me with Apostolis and Alexandros, my colleagues from ICCS, we enhanced the methodology of assess the buildings in a multi-hazard event, either being flood, urban heat, wildfire, or earthquake. The methodology that we devised follows, I hope that you can see it clearly in this slide. of building characteristics, historical remote sensing data, and sensors socioeconomic data, all of them together under a GIS workflow. We gathered data sets from pilots and from open sources, of course, stored them in a geodatabase, and performed various spatial analysis in order to estimate the vulnerability of the buildings under different hazard scenarios. To do this, we analyzed the buildings under and also the environment of the urban environment under 3 subsystems and 4 pillars, which I will explain in a little bit. So from the 3 subsystems, which were the buildings, the open spaces, and the population, we devised intrinsic vulnerabilities, which were basically different aspects of this kind of subsystems under the influence of the hazard that we are dealing with, and the exposed values, which were devised for 4 different exposed systems, which was the social, the physical, the structural, and the economic pillar. Together, they were combined under a combined vulnerability, which was normalized in order to be able to quantify the combination of these structures under a single combined vulnerability index. And finally, in order to see the impact of different hazard scenarios in the future, we devised the synthetic combined vulnerability, and we used as input from other partners the probability of hazard occurring for today, the baseline, and for future scenarios. So finally, we end up with the impact scenario. On that regard, I want to speak a little bit more about the intrinsic vulnerabilities that we devised. Here there are a lot of context about the overall methodology, which of course you can explore at your own time and see the data sets that we used. Here we have the application of the Spanish pilot for the urban heat, the Barcelona pilot. CIMNE provided us with extensive data sets, which are open source, and we encourage you to explore them for the cadastral and the social and the surface models of the city. So, as I mentioned before, we deal with 3 different intrinsic vulnerabilities on 3 on 3 subsystems. The building subsystems include information about the buildings, about their physical characteristics, about the land surface temperature during summer months, the solar exposure, the building volume, the year of construction of the building. So basically, the subsystem of the building is focused on the building characteristics. Then we have the subsystem of the open space. We created a buffer zone around the buildings in order to characterize the different characteristics of the open spaces that they have around them, either being a completely built environment, or they are being close to a park or to forests, or if they have shading, which we derived from the digital surface model. And so we estimated how vulnerable they are in terms of open spaces. Finally, we have the population subsystem, which we used census data sets like the purchasing power per capita, the average household income, unemployment rates, elderly population, or very young population. Vulnerable population were basically very problematic during extensive urban heat. We normalized this kind of data sets, and we aggregate them on the building level because we wanted to achieve the highest spatial resolution as possible. Following the intrinsic vulnerability, we devised the 4 exposed assets, which are the 4 pillars that I mentioned: the structural, the social, the economic, and the physical. Each exposed value was devised in order to showcase the exposure of each element. So basically, because we combine all elements of the building, of the open space and the population, we want to see how they react in different exposure pillars. Like the structural exposed values they were devised in a neighborhood level, and they were the structure, the percentage of structure built before 1970, for example. Or the social pillar was the percentage of elderly individual who suffer from extensive thermal stress. Or the economic one, which was the percentage of low-income households, and so forth. So again, we created the exposed values and we normalized them from 1 to 5, 5 being the worst and 1 being the best. The structural, the social, the economic, and the physical. Together with those, we combine them under a combined vulnerability and then a synthetic combined vulnerability in order to create the baseline scenario, which is, here you can explore the legend as well, which is basically the complete vulnerability assessment of a building throughout the 3 subsystems and the 4 pillars. Rina provided us with the future hazard scenarios for urban heat for 2050. So by using the probability of hazard occurring, we were able to project the synthetic combined vulnerability to 2050 for the RCP scenario 4.5, which is the most mediocre, let's say, scenario for the use of carbon and the climatic event, and for the RCP 8.5, which is the worst scenario, in order to be able to compare the synthetic combined vulnerability of present and of the future. So in that way, we were able to estimate a complete vulnerability assessment for the buildings for the hazard of urban heat. We plan to create similar maps for the other hazards and for the other pilots. We are currently developing the wildfire and earthquake pilot, which is the suburbs of Athens, and finally the flood pilots, which are the Senegalia and Ljubljana pilots, which are under development, but the final deliverable will be similar to the urban heat. So,
Jason, apologies, you're a bit over time, so if you can.
Sorry, yeah, I finished. So that was all from my side. Thank you for the time. I will be happy to answer any questions once we finish.
Thank you, Jason. Apologies for cutting you. After Laura, if you can share the screen again, please. Thanks. So after these 2 introductory presentations, we now delve into the specific use cases in which the solutions to such hazards are currently being tested. First of all, I want to present the Barcelona pilot, in which different services and solutions are being developed. We will speak about an inventory hub of building climate resilience measures and an urban heat resilience tool. So, speaking now from Barcelona studio of architect Pic Aguilera, I want to present to you innovation architect María Elena Céspedes Cuellar. So, when you're ready, you have the floor.
Thank you, Telmo. Hello, everyone. Today I will present the first pilot of the CLIMRES project located in Barcelona, Spain. This case study focuses on improving climate resilience in residential buildings, with particular attention to the Besós district, an area that faces significant exposure to urban heat and heat wave impact. I will start with the context and objectives of the pilot, then describe the selected building, and its main challenges. After that, I will present the proposed retrofitting measures, followed by the monitoring strategies and KPIs. And finally, I will cover resident engagement and social acceptance, and close with the role of the service S2 and S338. Next slide, please. So the Barcelona pilot, as said before, is located in the Besòs district. It was originally planned and constructed in the 50s, following principles of rationalism, low cost, and rapid construction. Although the area includes several building typologies, many of them share the same architectural and constructive characteristics. And a key issue that most buildings have is that they were not designed to respond to today's climate conditions, and they generally lack thermal insulation, and many windows are single glazed and without thermal breaks. As a result, residents are increasingly exposed to overheating, especially during heat wave periods. The main objectives of the Barcelona pilot is to improve the climate resilience of residential buildings, as said before. To achieve this, the pilot combines open data, on-site knowledge, technical analysis, and monitoring systems and resident engagement. The project identified vulnerable buildings, tests resilient measures, solutions, and evaluates their impact on thermal comfort. The approach is especially important because climate resilience is not only a technical challenge, but it also depends on how residents experience and accept this kind of interventions. So about the building, the selected building is located in Alphonse El Magnanin 44 in the Besòs district. It is a multifamily residential block with 6 floors and 24 dwellings in total. Each dwelling has an average of 50-55 square meters, and the main facades are oriented southwest and northeast, and the building is located close to the sea. This building was selected because it is part of an ongoing energy retrofitting program in the district, and it was an ideal case to CLIMRES to test this kind of solutions. So about the retrofitting interventions in this slide, the planned interventions that are ongoing include several actions related to energy performance, structural improvement, and accessibility. One of the main measures is the replacement of the existing exterior carpentry with systems that improve and provide better energy performance. The project also includes improvement to facade openings, roof renovations, the addition of thermal insulation on the street facades through ETIC systems, and the installation of facade balconies to shade control. Together, these actions aim to improve the building envelope and reduce indoor overheating, also improving general quality of the dwellings for the residents. About the monitoring, in addition of the pilot building, 3 nearby control buildings will be included in the monitoring system. These buildings are also located in the Besòs area and share similar construction system and materials. The control sample includes both rehabilitated and non-rehabilitated units, which allow the project to compare different building conditions. In this slide, a key component of the pilot is the indoor monitoring system. The monitoring period is planned from October of last year to June of next year, sorry. And the system will collect data from 11 dwellings in the pilot and the 4 dwellings in nearby buildings. And the variables are air temperature, relative humidity, and CO2 concentrations. These measures will be taken in the living room and the main bedrooms of each monitored dwelling. This information will allow the project team to assess indoor thermal comfort and indoor environmental quality, and evaluate how retrofitting process affects residents' comfort over time, especially during heat wave periods. And these impacts will be evaluated through these 5 KPIs that are seen in the slide. The next slide, please. So as said before, the resident engagement was central part of the Barcelona pilot. An initial meeting was held in the selected building to present the project objectives, the monitoring system, and the planned activities. The engagement strategy also includes door-to-door outreach using informational leaflets, like you can see in the slides. This leaflet was given to all the residents, and coordination with the building representatives that help the facilitation of communication with the residents. So in the next phases, satisfaction and usability questionnaires will be held, as well as interviews and co-creation sessions. Last, the pilot applies two key CLIMRES services, as said before, the inventory hub that works as a digital catalog, and the urban heat resilience service that focuses on a urban scale. Both services will be explained in more detail in the following slides. So about the inventory hub, in the next slide, please. The inventory hub for climate resilient buildings is a digital catalog and decision support tool designed to facilitate the design and retrofitting of buildings to improve the resilience to climate-related natural hazards. It improves an integrated user-friendly knowledge base where both citizens and construction specialists or professionals can access technical guidance, tools and reference materials to support an informed decision-making. In the next slide, you can see an overview of the service that is on ongoing development. The inventory hub homepage serves as the primary entry point of the platform. Here you can see at the top of the page, a fixed navigation bar provides direct access to the main section of the platforms, including the home, the three hazard-specific categories that are flood, heat waves, and wildfires/earthquakes, as well as the about page and contact page. Below this area, there is 3 cards that also correspond to these selected natural hazards. Further down in the same page, an overview of all measures available in the inventory hub is provided. A dedicated filter panel is located on the left-hand side of the interface, allowing users to refine displayed measures according to the natural hazard category, as well as qualitative indicators such as impact level, cost, or maintenance requirements. In the next slide, please. In this example, for example, the catalog is filtered to display only the heat waves related measures. So the results are given as a grid of cards, where each represents one measure and gives access to more information. Once you select a measure, it comes the measure page that provides a comprehensive structured information for each measure. First, a description outlines the main characteristics of this selected solution, and then a section of an implementation guide that summarizes key requirements and considerations for its application. Benefits and limitations section provides a balanced overview of the expected advantages alongside potential constraints or boundaries conditions that can affect this measure. And also the page includes a visual reference and optional to download a PDF summary of this information. Further down the page, you can have detailed parameters and data that is focused or aimed for the technical users that have the quantitative indicators. And this structured database enables comparison across measures as well. Finally, we have the About page, where users can learn more about the project, the CLIMRES project, as well as other services connected to climate resilient buildings and urban adaptation. That would be all from my side.
Hello, this is Gerard Moore from FIMNE, and I will speak about the urban heat vulnerability data inputs and modeling that we are using for the Service 33A. And then you will see a demo presented by Cardiff, by Carla. Okay, next slide. So the heat vulnerability index, we create this this platform from the point of view of indicators, and then from these indicators calculate indices in a similar way presented by Jason a few slides ago. But the idea follows the framework presented by IPCC in the third assessment report in 2001, which are these three main topics: the exposure, sensitivity, and adaptive capacity of, in this case, buildings and people who is living in buildings. And we create these 8 types of groups of indicators related to climate variability and extreme events, energy indicators, which could be, for instance, consumption or thermal demand in buildings, building characteristics, similar to the case presented by Jason. Next slide, please. Infrastructure indicators, providing information about the public services or even private services close to each building. Also, for instance, the climate shelters, which are quite important in this case. Health-related indicators. So we have we are dealing with data coming from public services that allows us to have information about access to primary centers or to the health system for cases related to heat in this case. We have also demographic indicators coming from the INE, the Instituto Nacional de Estadística, which is like the National Statistics Institute, and socioeconomic indicators like in household debt and household salaries and so on. So this is the data architecture that we are using and we implement during this project. So essentially the information, it's highly heterogeneous and in different formats and in different time scales and so on. We built many ingestors that could be current-fied or could be launched manually. And also, obviously, we are using API services to gather some of the data sets. We harmonize this data to an ontology, to a known ontology. And then we store this data into databases, a graph database and a time series database, because we are storing it as a knowledge graph, okay, based on this ontology. And then we launch each of the different types of modeling services that we implemented, mainly regarding to thermal demand of buildings, weather downscaling, and then a graph neural network to calculate some indicators for certain buildings that we don't have real data. And this data comes available to the database and through an API that we built in Go, in Go language. We communicate through the interface of CLIMRES. Okay, next slide, please. This is where I talk about the data ontology. So we essentially built internally in FIMNE and in coordination with other projects, an ontology that provides an order to the an important order to the data sets that we are gathering and are quite heterogeneous. And we, in this case, some of the most important features are the objects related to geospatial data, which in this case are could be aggregation levels or multiple aggregation levels, or buildings, building spaces, understanding building spaces as dwellings or so on. But this infrastructure, it's key for us to calculate these indicators in an easy and a standardized way. Okay, next one. Also, we open source some data gatherers. This is the Hypercadaster S library that through this link at the bottom part of the slide, you can see this repository. Essentially, we are downloading addresses, parcels, and building cadastral information from all cities around Spain. And we could integrate easily information about administrative levels, elevation data or data coming from OpenStreetMaps. And we perform an advanced geometry inference of the age of the buildings, and shading analysis for essentially for energy simulation data preparation. Next slide, please. This is SocialS library that also it's open sourced, and it's a way to gather information from INE, from the National Statistics Institute in Spain, in a standardized way. And you can obtain data from several of the data sets that are provided by them. And also we keep the focus on obtaining the data at the census tract aggregation level. Okay, next one. And this is the Green Shadow library, which is a more advanced library. It's more computational library in this case. It's from the LiDAR data, that we have for vast regions of Spain. In the case of Catalonia, we have the complete region with LiDAR flights, and then we calculate dynamic hill shading of this with this data, and we could obtain very detailed surface models of the territory that are important for calculating some indicators, such as the sky view factor, for instance. Next slide, please. Yeah, here I will present some of the models that we are using. The first is the weather downscaling model that we use essentially to downscale the data from the mesoscale scale. In this case, from ERA 5 or from Meteo Galicia WRF model, which provides us the 96-hour horizon forecast. But essentially, it's for downscaling mesoscale to 100-meter resolution for the case of Barcelona. And we use for doing so, we are using also the URBCLIM project datasets that were provided by Vito and Copernicus from 2008 to 2017. But here, as we have a model that could extrapolate to other time periods, we can obtain this 100 per 100 meters photo of temperature or raster of temperature and humidity in this case for other periods, and that's why it's interesting. This is open source data code also, so you can go inside and check on the details. Yeah, go. This is the thermal energy model of buildings. Here we used RC models, so the resistance and capacitance model, which is a simplified manner for calculating thermal dynamics in buildings. And essentially we calculate some archetypes around the city. And then we align each of these archetypes, which is each of the RC models, based on to each building, based on characteristics of buildings, energy systems, that we think that are placed on each of the buildings, the weather conditions, which also uses this downscaled meteorological data, and then some information from the people who is living in the buildings. Next slide, please. And finally, the last type of models that we are using, it's the graph neural networks, that we are using them for calculating attributes at each of the aggregation levels. In this case, buildings, districts, postal codes, census tract, whatever. When we don't have data from some of the buildings. Okay, so it's an interpolation problem where we are dealing with data that sometimes it's available at building level, sometimes it's available at some aggregation level. So there's a hierarchical forecasting problem here also that we are dealing with these graph neural networks.
Thank you, Julian.
Yeah.
Thanks a lot. And to finish up with the Barcelona case study, as we said, now Carla from Cardiff, who I already introduced before, will present the urban heat resilience tool.
Yeah, so very briefly, I will tell you a bit about the tool, which is built with all the data and indicators built from by CIMNE that Gerard has just explained. So this service has three main components. So the first one is the heatwave vulnerable areas mapping, which is to identify the most vulnerable areas to urban heat. Then we have a module for the strategic planning, so which adaptation measures should be prioritized. And then we have the early warning part, which is still built and work ongoing to see how cities can prepare or respond to heat waves. So the main functionalities which are already in place are the interactive heat vulnerability index map, which helps identify hotspots across the city. Then this building information panel, which helps us to explore vulnerability indicators for each building in the city. And then the resilience measures catalog, to explore these adaptation measures and with implementation guidance and examples. And then the future functionalities, so these are ongoing and still don't included in the tool demo that I will show now, are the scenario analysis. So to simulate these adaptation measures and evaluate the impact of the measures in the vulnerability index, and then the outdoor comfort measurement, which is being developed by another partner, UniVPN, and to visualize these outdoor thermal comfort conditions with real-time UTCI. So I will yes, now share my screen to go directly to the tool. Hope you can see it. Yes. So this is the main screen when you open the platform. So this is an interactive map. It displays this heatwave vulnerability index. This is the city of Barcelona, which is our pilot here in the project. And we can also explore the components, the main components of the heatwave vulnerability index by clicking here. So we have the exposure and the sensitivity and also the adaptive capacity. So we can see here the scale for these components, and below you can see there the different indicators that compose these three main layers. So we can see the heat index, and you can see there that the scale is quantitative in these cases. We can see also tropical nights or cooling degree days. For sensitivity, it's the same. We have this sensitivity, which is more related with indicators or socioeconomic, sociodemographic indicators. So this is the overall sensitivity index that is composed by these indicators, such as this population over 65 years, which is more vulnerable, as well as the population under 14. Or, for example, the number of people per household, and also the adaptive capacity. In this case, you can see that the color scale is different to highlight that in this case, the very high value is the positive one. So here we can see the adaptive capacity index, and you can see here also the vegetation coverage, but all other indicators such as the building cooling energy demand or the walking distance to climate shelter. So all these are combined into the heat wave vulnerability index, and we can also, as we were mentioned, explore a specific building in which we can see general information about it, the year of construction, the main use and the number of floors, also the geometry characteristics of the building, and then the resilience to heat waves, so the indicators. The heat wave vulnerability index with its three components, and then it is prepared to integrate the upcoming following components. And if we go to the catalog part, we can also explore the Resilience Measure Catalog Explorer, which contains a lot of measures. They can be filtered by the type of intervention, such as open space. We can see also the applicability of the measures or implementation time. It can be filtered, for example, measures that can be implemented in a short term, or measures that have a very high impact when implemented, as well as the cost, if we only want to see low cost measures or low maintenance measures. And for example, if we go to a measure, we can see the description, implementation guide, and then the advantages. We can go also to technical features. And there's also these case studies and examples, so we can click to see more details about these examples, and also the reference and resources for it. So this is all in all the catalog, and yeah, I think it serves to give an idea for the tool. Stop sharing.
Okay, thank you, Carla. It was very interesting, and thank you also, Gerard and Marita for your presentation and for showcasing what the Barcelona pilot is doing. Next, if you can share your screen again, Laura, please. As we have mentioned, other hazards that are increasingly threatening European cities are wildfires and earthquakes. And these have significantly risen in the recent years in Greece, and given its hot, dry summers and its location on active tectonic fault zones in the eastern Mediterranean. So to address this, what is the Athens pilot doing? Please, Penny Kazaki, head of EU projects as Sustainable City Network, or SCN. The floor is yours.
Thank you. Good morning also from my side. In this presentation, I will briefly introduce the Greek pilot of the CLIMRES project, focusing mostly on the pilot locations, the risks we are addressing, and the methodologies being deployed to strengthen both fire resilience and the structural and seismic resilience. The pilot is particularly relevant for Attica region. We say sometimes it's the Athens pilot, but actually the pilot sites are around Athens, because it brings together real local risks, real municipal infrastructure, and practical tools. So in this slide, you can see the overall scope of the Greek pilot. Our aim is first to gain insights from areas that have already experienced intense wildfire and earthquakes and which remain highly exposed to future risks. Second, we want to use vulnerability assessment techniques to support more informed decisions, especially in relation to fire prevention and response strategies. And third, the pilot includes the deployment of innovative technologies around two main services: the structural and seismic resilience service and the fire resilience and detection service. An important component here is the integration of IoT sensors, which allow real-time data visualization and make risk information more operational for local authorities. The first location of the Greek pilot is the town hall of Kifissia in the municipality of Kifissia. This is a highly relevant site because the municipality is directly exposed to wildfire risk from Mount Penteli, which lies on its eastern side. Kifissia has a population of more than 700 inhabitants, and since 1981, the area has experienced 14 wildfires, with some of the most severe events taking place from 1995 to 2024. What's particularly striking is that in 2024, the wildfire came within approximately 2 kilometers of the town hall, so it was really, really close. This underlines that wildfire risks is not limited to forest, but also threatens urban areas and critical municipal buildings. Here we can see the second location. It's a school in Thrakomakedones in the municipality of Acharnes. This site is particularly significant because schools are highly sensitive public buildings. They are places where safety, preparedness, and continuity of operation are essential. Given its proximity to wildfire-prone areas and its location in a municipality with strong seismic history, this site is ideal for demonstrating how the pilot can support both fire resilience and structural resilience. Next slide, please. Here we can see the actual town hall, the first location. So as you can see, then the town hall was selected as it is a very important building, not only for operational reasons, but also for, for prestige, let's say. Sorry, thank you. The site is really close to the Mount Pedeli, so it was really important for the municipality to be able to make it, let's say, resilient in the first case. So that's why it was selected. In the next slide, we can see, thank you, the installation of the equipment. The installation took place in the last days of April 2026, alongside with the installation in the other sites. If you can go to the next slide. Okay, here we can see the school in Thrakomakedones. This site is particularly significant because schools are highly sensitive buildings, and it was a perfect place to demonstrate how the pilot can support both fire resilience and structural resilience. So this school, it is not just, let's say, a test location, it is also a strong example of the type of public infrastructure that need integrated protection from climate and disaster-prone areas. Here you can also see the equipment installation in a harness. As in Kifisia, the installation of the equipment took place in the last days of April 2026, marking an important milestone from the Greek pilot. We go with the installation, we go, next, previous slide, please. Thank you. We go from planning to actual implementation, and it's a critical milestone for the practical testing of the CLIMRES approach. So this is all from my side. In the next two speakers, will give you more details about the services that we are using in the Greek pilot. Thank you.
Thank you very much, Penny. As you see, to delve more specifically into each of these hazards, as Penny said, we will have two speakers. And firstly, we have Professor Petros Christou from the Frederick University and Frederick Research Center, who will be presenting the seismic resilience service being developed in the CLIMRES project. So when you're ready.
Good morning from my side. Thank you, Telmo, for the introduction. I'm here to present the structural and seismic resilience service, which aims to support seismic vulnerability assessment and risk-informed decision-making by transforming building level information into actionable indicators of seismic risk. This service combines building inventory data, engineering-based vulnerability assessment methods, and scenario analysis tools to generate information that can assist municipalities, civil protection authorities, and policymakers for improving preparedness, etc. So in this presentation, we will focus on the need for the service, for the potential users, the service flow, and of course, the results. And I want at this point to also acknowledge the people from FRC who contribute to the realization of this service. Next slide, please. So in this slide, we see the final product. It is a spatial representation of seismic vulnerability and expected damage for a selected earthquake scenario. It has to be a scenario for this to work. This visual is called a seismic risk map, and it provides a visual of potential impacts of an earthquake and allow users to identify areas that may require further action, much like any other service. It includes, this action may include preparedness planning, resource allocation, resilience planning, and possibly prioritization and mitigation measures. I should say that this tool is not to replace any detailed engineering study, but it's rather an evidence-based tool that supports planning and decision making. Next slide, please. So the outputs, as mentioned, are directed or geared towards municipal authorities, which they can use use this information to better understand vulnerability of their building stock. Civil protection authorities, they can use this to support emergency preparedness planning or improve their understanding of potential consequences based on different scenarios, as mentioned earlier, and of course, policymakers. So although the needs for these groups differ, they can all benefit from this. Okay, let's stay on this slide. So to understand how we reach this result, this is just a brief workflow of the service, which begins from the inventory development. These are the individual building level. That means the collection of data has to be building by building, which is painful at times. These buildings are then classified according to taxonomy, and then associated with some vulnerability and fragility models. Then the user can or has to select a scenario, and then based on the scenario, the service is going to estimate expected damage and present those visualization tools like these maps. Can you go to the next slide, please? So the building inventory that we have to develop represents possibly the most important component of this service. Unlike some other, let's say, resilience assessment services, which rely on large-scale environmental data sets or satellite observations, and so on. This service, as mentioned, is initiated at the building level, and the process starts there. The information that needs to be collected includes structural material, construction period, number of stories, etc. And then this information is organized and stored in this inventory database. And following that, these buildings are classified using a taxonomy, which serves as the bridge, if I can use this, between the collected information and the engineering assessment methods. So this taxonomy is a major part of this part. Yeah, next slide, please. So the interface of the service allows the users to define an area of interest, obviously, select an earthquake scenario, has to be selected, and then choose different ways of visualizing the result. The design philosophy of this interface is to provide access to whatever sophisticated assessment capabilities of the service through a relatively simple and intuitive user environment. And the intention is to have users concentrating on creating scenarios and interpreting results rather than messing with the engineering calculations or anything else that is related. Can we move on, please? Okay, so the engineering results of the service are presented through damage states assessment results. This service estimates the probability of exceeding different damage states. That's the graph on the left. The different colors are different damage states from slight all the way to complete damage levels. And then for different earthquake scenarios, that's the horizontal graph of this, the horizontal axis of this graph. So sliding back and forth on this, we essentially visualize a scenario and the different damage levels related to that. Let's move on, please. There are different ways of visualizing the results for different spatial scales, I should say. For example, we could visualize this thing on a building by building level. However, this is not suggested. It's much better to provide the data in a larger scale, in grids, for example, 200, 250 meters of grids, so we can facilitate comparisons between areas and then help the users to identify patterns of vulnerability. So this flexibility allows for a range of applications. Next slide, please. So up to now, we have done different things. Some of them are completed, some are pending. For example, building taxonomy, fragility functions, all these things are completed. Same with the survey methodology, which is, I should say, a structured methodology. So there is a tool that was developed for this reason. The database structure, which is also up and running, and the system integration thing is almost complete, if not complete at all. And now we are focusing on populating our database, our inventory, because based on that is going to depend on the any credibility of the service. And then the final slide If you can move on, please. In conclusion, just to say that this service is providing actually a framework for transforming this building level information into an actionable seismic vulnerability and risk indicators. It goes from the integration of building inventories to taxonomy, classification, to fragility functions, and then to scenarios analysis through visual representation of the results. So that's all for me. Hopefully, this was interesting. Of course, if there are any questions, we can discuss later. Thank you.
Thank you very much, Petros. To the other experiment that we've been mentioning throughout the webinar, and there is the last one that we will focus on today, is the wildfires risk, which is ever more increasing over the last years in many parts of the Mediterranean. For this, Justinos Sabris, project manager at Movix, will present the fire resilience tool. When you're ready.
Thank you, Telmo. Greetings, everybody. I'm Justinos Sabris, and I lead the fire resilience service inside CLIMRES. The next few minutes are going to be about what this service is, what it does for a municipality on days before the fire, hours during the fire, and months after it. So next slide, one before. Okay, here, sorry. So Penny basically set the scene earlier. In 2024, Attica fire stopped 2 kilometers from a town hall, and that in one sentence is the wildland urban interface problem. And it's the problem the service was built around. The CLIMRES Fire Resilience Service is a decision support platform. It combines satellite imagery, ground sensor network, a data management platform, and AI models that turn all of that into something a municipality can actually act on, not just a dashboard, an evidence base for prevention, response, and recovery. Next slide, please. Oh, sorry, this one is okay. The before, one before. There you go. So the service is organized around the 3 phases of a fire event, mainly because this is how municipalities actually experience one. Before, we help municipalities know where the risk is so they can plan ahead, pre-position resources, and also clear fuel from the ground where it matters most. During the fire, we give eyes on the ground in real time, and we put that activity on top of things that they care about, which is infrastructure or resources that help with firefighting. And then after, basically, we help with measuring damage objectively, and then keep tracking of recovery over months or years, so that reforestation effort can actually be claimed. Next slide, please. So we built this around the three main groups of users: local authorities and municipalities, civil protection at the national and regional level, and emergency responders on the ground, fire services, search and rescue teams, or volunteer networks that show up first. Different views like the application, the app basically has different views per role, but there's one shared map underneath. And if anybody in this webinar is one of these 3, then this tool is built for you, and we would love some feedback later on. So let's actually go to the application. Next slide, please. So the first part is the before, as we said. The central output here is our CLIMRES Fire Risk Index. It's an operational risk surface over your municipality with 5 levels from very low to very high. It's built by fusing satellite signals, vegetation health, vegetation moisture, fuel type of the ground, and the fire weather index, which is being pulled and parsed real time. We can move to the video so that people can understand. There you go. So on top of as you can see here, you can see here the fire risk map with all the indexes. And on top of the risk map, you have this, there's fire risk and also the individual, like the two main components, raster files that constitute this index map. And very importantly, on top of the risk map, there's a layer of operational assets. So it's some critical infrastructure as well as water sources for firefighting sources or even natural water reserves. This is kind of like a filtered information for that type of view, but later on there's more granularity to what the users can see. So what you saw here is the fire risk index overlaid over an area of interest, and we can move to the next one, which is also part of the before aspect. It's a fire simulation. It basically allows for the municipalities to run a few models in terms of how fire spreads given the weather conditions, elevation conditions, fuel map, fuel type of a specific area, and obviously like wind direction and speed. We can move to the video. So there you go. So basically, by setting an ignition point and some parameters, basically you can watch how the fire spreads on 5 minutes increments, which basically gives an overview and some serious understanding of which areas are more vulnerable. We can move to the next slide. And this is the during part, which is essentially I would say like a operations control panel, and it's where also most of our our infrastructure takes place and adds value. So we have set, as Penny said before, cameras and IoT sensors to key strategic points so that we can have some alerts for early detection of fires. And this is always apparent at the administration level. So as I said, the first piece is a camera network and a network of carbon dioxide and temperature sensors within the forest or nearby dense vegetation. When an alert fires, the operator doesn't just get a message, they get the alert stream, the actual camera snapshot, and there's an option to verify true or false for basically avoiding false alarms. And this is where everything starts. Then every alert lives on the operations map, which is layered on top of the events, and it's basically resources, sensors. We can go to the video as well. So basically, there's the municipality or the civil service the correspondents. Basically, they can see resources like trucks, water deposits, even volunteer teams, as well as critical infrastructure and water sources. Every alert. Sorry. So the question is basically never where it's just a fire. If there's a fire, what's the risk in the next 30 minutes? So basically, what is the first steps that a respondent does when they have an alert? So to the next part of the application is the after phase, which is the phase that most tools forget. When the fire is out, the cameras stop reporting and the dashboard goes quiet. CLIMRES, the fire resilience service, does not. Basically, what we want to do here, first of all, is the damage extent. We compare satellite imagery over time from before the fire to after the fire, and on a weekly basis, so we can estimate the burned area objectively. That's something very useful for reporting and funding requests. Another interesting piece is recovery monitoring. So basically, you can designate an area of interest, maybe a rehabilitation zone, for example, and CLIMRES keeps watching this area, tracking vegetation regrowth from the satellites, and on top of that, an extra layer of key activities onto a timeline, so that the municipality can actually have an overview of, whether some of the activities had an effect. For example, like clearing debris or replanting or volunteer reforestation activities, etc. So to the general plumbing, we basically most of it I've already explained. We have some basic feeds, European Union satellite imagery from Copernicus and Sentinel. Our ground sensor and camera network are our main data input. And then obviously we have the weather data, including the fire weather index, which we mostly use from EFIS, with another European project. The platform handles the heavy lifting, artificial intelligence, and for the risk modeling, spread simulation for mapping and alerting, and also a data management platform for each municipality to flexibly add the resources or critical infrastructure as they may. And the output essentially is, as I said before, the fire risk index, real-time alerts, recovery timeline, and an operations map. So what is next for the following months is we've installed all the sensors in the pilots, and basically we're starting the pilots in a couple of weeks. We're aiming for better and more granular input data. Also, we want to, based on some feedback, we want to start investigating whether we can have some detection of private pools as an auxiliary firefighting means, because if municipalities know that they can have some extra auxiliary deposits near fire risk areas, they would actually plan ahead to do the proper installations. Also, we want to work a little bit more on the data for better distinction of wildlife density in peri-urban areas. The signal is very oftenly noisy because of the coexistence of buildings and vegetation. And then we also want to enhance the fire risk index by using climate projected forecasts. And essentially, we want to see that taking place into other municipalities, which we have identified that would be perfect for these scenarios that we are solving. Thank you very much.
Thank you, Justinos, and thank you to all the speakers for your presentations. Although brief and we didn't have so much time to delve into each of these specific tools with detail, I see that these are very promising, or I have the feeling at least that these are very promising solutions that are being developed. And the goal now should be to achieve the adoption of these tools and solutions by a wider level than the project. For this, we need the involvement of developers, property owners, and also with special attention, we would need cities. European cities, since you are the ones that can implement these solutions. Because of this, we would like to learn about your interest in these solutions and in the CLIMRES solutions, and how you believe this can be implemented in your cases. With this, we start now a Q&A session. So please, if you have any comments or any questions, feel free to unmute yourselves, or maybe raise your hand first, or write them in the chat. I see that we've already had some questions and that Carla kindly has been answering. If you want to extend on those or say anything at all, or anybody else, I mean. So yes, Xavier?
Yes, hello everyone. Thank you for the presentation. I have one question about the heatwaves tool. Is there any function that allow a user to know directly what is the best solution if he gives one indicator? For example, I want the best solution to reduce only the temperature. So does your tool can calculate directly what will be the best solution for this?
Not yet, and we will explore this because yeah, I was also answering to the question of the adaptation measure simulation. So we are working on trying to make the catalog kind of applicable to the buildings in the city. So trying to see what is the impact of the measures in the catalog to reduce the heat vulnerable index. So while we are working on this, we can explore also this kind of a more straightforward recommendation for a building. I don't know, the most impactful measure to apply to this building to reduce this heat vulnerable index, or yeah, maybe the most cost-effective measure or so, but this is not yet implemented in the tool. We are working on this.
I see that Andrea Enriquez also wrote in the chat, I guess a question that it's could be better answered by the Athens pilot. So, in your experience, which adaptation measures on a building level for fire and earthquake have been the most practicable in real life? If anyone can answer.
I could provide the perspective, let's say, as we are collaborating very closely with municipalities. So real-time alerts are, I think it's the most important for them. And to be able, to detect, see, and let's say, proceed with the evacuation. I think this is the most important in our experience, because wildfires is a really big problem the recent years, and I really believe that it's going to be a really serious problem also the next decade. I'm not sure if anybody else has a comment.
If I can comment at least on the earthquake service, considering that we cannot predict when the earthquake is going to happen and also where. The intention of services like this is to provide tools that allow for informed strategic decisions with regards to what has to be done in the preparation level, and then maybe any mitigation measures after. So even if at least this service, I mean the earthquake service, even if it is built around a database or an inventory which is, or it has to be at the building level, the results cannot be taken as such. In other words, this is not an intention to intervene on a building level. That would require detailed engineering work, but rather is to provide a probabilistic tool which is going to, let's say, assist and guiding actions with regards to where is the more vulnerable areas, and do some kind of comparisons and make decisions regarding, let's say, budget allocation, evacuation routes, even changes in the municipality planning if such a measure is required. I don't know if that answer the question, at least, or the concern.
So thank you. I don't know if we have any more comments or questions. Andrea says thank you for the answers. So we'll have no more comments. I'll thank the speakers first for your insightful presentations and for your availability and disponibility to present today. And then to everyone who joined, I hope this was useful. And as we said, this is the first webinar of a webinar series that we will be promoting over the next months. It will consist in total of 4 webinars and will happen from now until the end of the year. So mostly all happening in autumn. Thank you everyone, and enjoy the rest of the day and the rest of the week.